in half an hour to 1 hour, we'll just take a basic session on the case structure and what are some of the important things to just see while doing a simulation in OpenFOAM. Okay. So now, once you've done your installation, most of you must have tested out whether your installation is working fine. For those of you who are facing some issues, you can always email us and we will try to resolve your queries in the email itself because we passed the installation phase. So now when you're starting with OpenFOAM, the very first case we always tell people to learn is your cavity case. So if you're going for OpenFOAM 9, I'll show you for OpenFOAM 9 and for 2412, where can you find the tutorials and all. So for OpenFOAM 9, you have the OPT folder. Within OPT, you have OpenFOAM 9, and under OpenFOAM 9, you have tutorial files. Okay. So this is where you will have all of your base tutorials saved. Once you install, then you can just copy paste any of these tutorials into your run directory and modify it according to your case. So for our case now, we will take the incompressible tutorial. In incompressible, we have something known as IRWCFD. IRWCFD is just your incompressible foam solver. So you have your incompressible solver. And within this, we have the cavity case. And again, inside that, you have another cavity case. So see, this is your base case, zero constant system. Okay. So let's copy this particular case into our run directory. So we'll go back to home and in that OpenFOAM, and then you copy it into OpenFOAM 9. Now I have multiple versions, that's why it is showing those additional files. But if you have just installed it first time, you will just have one particular file. Okay. So don't really bother too much with how many files I have and how many are there on your system. It keeps changing every time. So let's paste it over here. Okay. So I've pasted within FOSSEE. So we have this cavity case. And now we have, as I said, in the very first PPT that we have a base that is zero constant system. Zero is where you will have your initial boundary conditions. Okay. So have you all understood till copying and where your tutorial files are saved? Just give a thumbs up. So I'll show the tutorials also where they are. So once you open your Ubuntu on the left hand side at the very bottom, you have Ubuntu 2204. So you can open that. And for OpenFOAM 9, you have the OPT file. So as I was saying, in Ubuntu, you have your OPT folder. Within OPT, you will have OpenFOAM 9. Within this, you have your tutorial folder. Okay. So in this tutorial folder, you will have a number of tutorials. So there are your basic tutorials, as you can say that in the morning, what we did, scalar, transport, foam, and all those. So those are your basic. Then you have some combustion related solvers as well. So for people who are asking whether you can do combustion in OpenFOAM, yes, you can do combustion. You have multiple solvers. You can always try these. And in OpenFOAM 9, there are a few. But when you are going with OpenFOAM 2412, there are multiple options you have in tutorials as well as solvers. That's why we've told you to install 9 and 2412, because if you want to do a little bit more complex simulations, we always prefer 2412 because it has much of the solvers and those solvers are a bit stable compared to OpenFOAM 9. So in OpenFOAM 9, we will first copy an incompressible solver or a tutorial. So under incompressible, you have a number of solvers again and tutorials. So we will take the IRWCFD. Okay. So your incompressible foam. So we have IRWCFD. Under this, you have a cavity folder. And within this, you have one more cavity folder. So we'll be copying this particular cavity folder. Okay. So I've copied this already into our run directory. So you can go back to home, your name, OpenFOAM and OpenFOAM 9. And within this, you have your run directory. Okay. Now in run directory, I have made multiple folders. So I'll just save it into one of these folders. So over here, I have one case, FOSSEE, and inside that cavity. Okay. So now in this cavity case, as I mentioned previously, you have three main folders, your zero, constant, and system. Now in your zero folder, whenever you copy, you'll have these additional zone identifiers on Windows. If you're on Linux, you won't have this problem. So you can delete those zone identifiers or you can leave them as it is. It won't give you that much of a problem. Okay. So in your cavity case, you will have zero, constant, and system. Your zero will have your initial boundary conditions. So you'll have velocity, pressure. If you want temperature, you'll have another temperature file. If you have, like we had scalar 1, scalar 2, in multi-phase you saw that we had a special file for air, for water. So depending on the tutorial you're trying to solve or the case that you have, these initial boundary conditions will change. But for the very basic cases, you will always have your velocity and pressure, and for some cases temperature. So these three files are the very basic ones. Okay, so you will have these files. So let's open one of these. So you can, for people who don't have VS Code or any of the thing, you can open it in Notepad. It's not a problem. Okay. So we'll open this one in Notepad. So again, in Notepad, once you open, as I mentioned in the programmer's guide, you have the dimensions. Now, if you're starting off, you don't really need to pay that much attention to the dimensions. You just need to make sure that they correspond to the proper unit that you have. So this is where you have your dimensions. You can always refer to the programmer's guide. Like as I said, first one gives you length, mass, time, all of those things, temperature, and all those things. Then you have your internal field and you have your boundary field. Now your internal field, you can think of it as a flow inside. Like if you have a box, you have a flow already initialized and kept. So now now currently you will have an internal flow of 0. But if I were to change my moving wall, now suppose on top we have like in this particular case, I'll draw it and show you. Let's open paint. So in our particular case, the one that we've copied now, the cavity case. So what is happening in this case is you have, this is your domain. Okay, you have walls, this part, and this part. These three are walls. Okay, it's a 2D case, so you don't need to bother that much in the Z direction. So these three are walls, and the top one is a moving wall. So you will have a velocity. It is like, you can think of it as if you have a box and you are sliding the lid, like sliding the lid in the X direction up to infinity. So this is what this case is actually doing. You have this top lid that is moving in the X direction, positive X direction. Okay. So ideally, when you have a case like this, you would have some flow, since only the top is moving and these three are walls. Once you reach this side, it will hit this wall. Once you reach this side, it will again hit this wall. It will hit this wall and it'll keep circulating within this. Okay. So this is the flow that we're going after in this particular tutorial. So by understanding how this flow is happening, you can see that in a boundary field, we have moving wall and we have fixed walls. And you have the front and back. Now, since it's the 2D case, we are leaving it as empty. So in the moving wall, we have given the value fixed type. Now Nikhil has explained most of the boundary condition and boundary types that we are using. So we need not go too much into detail. So fixed value in simple terms is just you're giving a value in the X, Y, Z direction. Okay, so you'll have a uniform field and you have their coordinate system. So we are giving the value in the X direction, positive X direction, as 1 meter per second. Okay. And at the fixed walls, we are giving no slip condition, meaning that if anything were to hit that wall, closer to the wall, it will stick. That is like in your real world scenario. Closer to the walls, you will always have a boundary layer forming. So for those reasons, we use no slip condition. But in certain cases, you might want to use, say, slip condition for it to act like an artificial wall that does not exist. It's just there for like a channel case. In those, we usually use slip condition so that the walls do not affect anything of the flow. Or you can use the slip condition, no slip condition, which will basically form your boundary layer. And depending on the case, you can change these. Now, if I were to make it an open domain, I would use symmetry conditions or zero gradient. So those are your far field conditions. So again, depending on the case that you have, you can change these. We need not go too much into detail for this. So we have a velocity in the positive X direction according to this, okay, with 1 meter per second. Now, this is your velocity. Okay, I'll keep this open. Then we go to our pressure. Okay, yeah. So now in pressure, again, you can check the dimensions. Over here it is mentioned internal field uniform 0, and in the moving wall we've kept everything to 0 gradient. Okay. Now for pressure, usually we do not go too much into it because it's a velocity driven case. If you were to have a compressible, or you're looking after shock waves and all of these parameters, in which your pressure, temperature, velocity, all of these parameters are really important, in those cases you will be changing all of these flows, all of these parameters. But in the cavity case, it's a very simple case. You don't need to really change anything. You can, if you want to just learn something about OpenFOAM and you just want to start off, you can try modifying this cavity case, and you can try increasing the velocity and see what exactly happens. It's a good test to understand what exactly is happening in your domain. So this is your velocity and pressure, two of your initial boundary conditions in your zero folder. Then coming to the constant folder, you will have the transport properties. Now, so ideally it will look something like this. You just have your new parameter, okay? Your kinematic viscosity. Most of the simulations, if it is a flow simulation, will just ask you your kinematic viscosity. Certain cases might ask you your dynamic viscosity and some additional parameters. Like in our case, when we were solving for scalar, we required to give the thermal diffusivity, thermal conductivity, all of those parameters. But in these pretty simple cases, you just have to specify your viscosity of your fluid, and then you can move on. Now your viscosity, you can base it on your Reynolds number. So say if I were to run a Reynolds number of say 100, so I would change my velocity or I would change my viscosity. So either of those, you can tweak these to get your Reynolds number or the range of Reynolds number that you're looking for. Okay, so this is your transport properties. And if you were to run a turbulent case, you would have another file that would be turbulent properties or momentum transport properties. Those will those will give you just additional parameters of whether you want to switch turbulence on or off. That's the only thing that's going to do. And in that, you can also specify which turbulence model you want to use. Now in OpenFOAM, we do have the RANS model. You also have URANS. You have multiple. You have K omega SHT, many K epsilon also you have. So depending on what you want to solve, you can always incorporate those files as well. And then we have our system folder. Now in system, we have the block mesh, control dict, FV schemes, and FV solutions. So let's open one by one. We have our block mesh. Make it full screen. So in block mesh, the very first line we would have is convert to meters. What this does is it is just going to divide all your values by a factor over here, whatever you mention over here. So if I were to keep this as just 1, any values that I've put over here, it will just be 1 meter. If I were to put it as 0.1, it will divide everything by that number. It will basically multiply everything with this number. Okay, so let's keep it as 0.1. Vertices, now we have many workshops on block mesh itself. We also have spoken tutorials. So you can see those to better understand how to define a block and how to create a block or a mesh using block mesh. So to make things very simple, we'll just draw it on paint over here. So now we have the points 0.0, basically 0, 0, 0. This is your XYZ coordinate. So let's make a new. Okay. So at say this is my XY coordinate. Okay. This is Y, this is X. So we are putting 1 point at 0. That is over here. So we have 1 point over here. This says 0 at your origin. And the next point is at a distance of 1 in the X direction. And the next one is at a distance of X and Y. The next one is only at a distance of Y. So this is one, you've made 4 points, and then you join these 4 points using this hex coordinate system. Okay. Now in block mesh, you would require to make a proper hexahedron. Okay. That means you need to have 4, no, not 4, you'll need to have 4 points in the front, 4 points in the back. That makes a total of 8 points. And you would need to have in total 6 faces, correct? So you would have something like this. If you see these coordinate systems, you can just correlate them with this particular drawing. So over here we see that this first front point, or the back one, you can say, okay, we'll take the back one. The back one is the origin. So we have these particular 4 points that we had made. And then with the depth of say 0.1 in the Z direction, we've put these 4 points. Now we've mentioned this 0, 1, 2, 3. Okay. So these correspond to the coordinate system that you have mentioned over here in your vertices. So you can say this as 0. This is 1. This is 2, and so on and so forth. Okay. You get the idea. So over here, what we're doing is we are mentioning that these points have to be or like put in this particular order 0, 1, 2, 3, 4, 5, 6. That makes up one block. Okay. So this is 0, this is 1, this is 2, this is 3. Then you replicate or mirror the exact same thing. So corresponding to 0, you'll have 4. Here you would have 5. Here you would have 6. And here you would have 7. So that makes a total of 8 points. Okay. Now, once you're done mentioning your or defining your whole block, then you move on to the cell size. You're going to define the cells within that block. So over here, you have again the XYZ coordinate. Everything over here follows the XYZ coordinate system. Okay. Leaving the boundary part. Okay. So over here, you would have X direction cells, Y direction cells, and Z direction cells. So over here, we specified 20 by 20, and in the Z direction, we only want one cell because we are just solving for a 2D case. If you're solving for a 3D case, you will mention this over here also. And simple grading as 1, 1, 1. Now your grading is similar to inflation, like how we use inflation in ANSYS. So if I were to change, we can change this as well. So first let's keep it at default. I'll show you the mesh itself. Okay. So might as well do that right now. So let's say we open in terminal. OF9. And first I do block mesh. Okay. So my mesh is done. Show you in ParaView. Okay. So this is a simple geometry. Okay. As I showed you, in your X and Y direction, we have 20 cells, and in the Z direction, we just have one cell. Okay. Now, if I were to change this grading, so say in the X direction, I want a grading of 2. Now your grading, your simple grading is just a ratio of your last cell to the first cell. So when I type over here 2, it means that it is your last cell to the first cell, right? So that means my last cell will be 2 times as that to my first cell. Okay. So it's a ratio. So if I were to save this and again do block mesh, ParaFoam. So you see, my last cell is 2 times of my first cell. So depending on the ratio or how coarse or how fine you want your mesh, you can change that parameter. Okay. So let's keep this as 1. Now there is something known as multi-grading as well. If time permits, I might show you that as well. Multi-grading is handy for cases in which you don't want to split your domain into multiple blocks, because now see if you were to now for our particular case, we know that at the walls we are going to have some boundary layer formation and all, so might as well increase the mesh closer to the walls. But if you do that, you would have to break down the domain into multiple blocks. Okay, if you're doing simple grading. But with multi-grading, what you can do is, again back to the drawing board. So suppose this is your domain. If you were to make a mesh closer to the wall, now with this particular simple grading, all my mesh went towards the left, right? So here we had fine mesh, and then here it became coarse. But with multi-grading, you can define, like you can split this entire line or your entire X direction into multiple parts. So I can say that I want in this corner, I want fine mesh. In this corner also, I want fine mesh. And as you move towards the center, I want it to be coarse. So multi-grading gives you that ability to manipulate that whole block as per how you want it. And you can use less number of blocks because of this. So that is what your multi-grading is there for. We have a specific tutorial on that as well. So you can always go and check that out. Okay. So once you've defined your block, you have to give a boundary name. Okay. Otherwise, you won't be able to add your boundary conditions or anything like that. You just have a simple block. So this is where your boundary comes into play. Okay. We can ignore edges for now. We'll not go too much into that. Edges basically help you create curves or any arcs or something like that. So if you want to create a circle, you can do that using this edge part. But again, edge to explain the whole thing, it will take another 15-20 minutes. So let's keep that on hold. So we'll go down to the boundary part. So boundary, you have again the moving wall, fixed wall, and front and back. Now in your boundary, we have to specify this. You know the right hand thumb rule, right? So you apply the boundary, you apply your face name or numbering based on that right hand thumb rule. Now, in our case, we have the moving wall to the top, right? So over here we have the moving wall. So if I were to keep my hand on this top face with my thumb pointing outward and my fingers curling this thumb, okay, so we would have it curling this way. So you can say counterclockwise. Okay. So we would name this as 3762. That is the labeling scheme that we follow in block mesh. Okay. So that's why over here the numbering is 3762. Points number 3762 make up this particular face. This particular face is your moving wall. Then same goes for the fixed walls. Now this one, if my finger was pointing outward and my fingers are curling around it, it would be something like this, right? So if I'm looking at it, it'll look like clockwise. So it would be 0473. So it's 0473. Same for this side, it would be 2651. And if it's for the front or for the bottom face, it would be the same, like 1540. And for front and back, again, the same thing. It's just that this time the type will be empty because we are solving for a 2D case. It is your empty type is just that we are expanding the whole domain in the Z direction up to infinity. So that makes, in simple terms, your whole geometry a 2D geometry because we do not have any circulation or anything forming in that Z direction. If you were to solve for a 3D case, obviously this will change. You'll just put it as wall or patch or something like that. Okay. Now in our case, we have all of these as wall. You can change this to patch. There are multiple options. There is patch, there is symmetry, there is wedge. So in a wedge, when you have a circular domain, like if you have a pipe and you don't want to simulate the whole pipe because sometimes simulating the whole pipe might be computationally very expensive. So you only take a section of that pipe and you define it as a wedge. So you can do that whole thing. You can simulate that whole wedge with the properties of a whole pipe. Okay. So those are different types or ways you can model the whole thing. So depending on your use case, you can change those things. So this is about block mesh. Then, then we go to control dict. Again, as I said, this is where you will mention your start time, end time, notepad. Yeah. So this is where you will mention your start time, end time, the application like IRWCFD. Then you would have end time, time step. If you were to introduce any post-processing data, like for an airfoil case, for all the people from aerospace engineering, if you want to find the coefficient of lift or drag, you can add those additional functions at the end of this control dict. Like you would have a functions part, like you would write functions, and then you would put a whole syntax block over there. So there are multiple ways to like those parameters and you can use to post process something. So if you want, you can remove the wall shear stress, or you can remove wall temperatures. You can remove coefficient of lift, drag, multiple parameters. So whatever you want to post process are always put within this control dict. So this is your control dict. Then we have FV schemes and FV solutions. I think Nikhil has already covered this. He had mentioned the Gauss linear and Gauss Seidel schemes and all of those. So here we are using the Eulerian scheme. So this one is a transient solver. That's why using Eulerian methods. If you were to use simple form, that is a steady state solver. So it would have the written steady state instead of Euler. So again, these are the FE schemes and solutions. In solutions, you mention your relaxation parameters, any of these parameters if you want to tweak. Like if you have some of your solutions diverging, we usually try to tweak all of these within this. You can add correctors, orthogonal correctors, and all of those. So if you have done already a basic CFD course, you will understand what are these doing and why we need to change some of them for a particular simulation. Okay. So once you're done with everything like this, you can now see this case does not have an all run file. So there is a thumb rule while running your case, anything in CFD or simulation. Okay. First, you start with the geometry, then you start with the mesh, then you go ahead with your simulation or the running of the simulation itself, and then you have your post processing. Okay. This is just a thumb rule. You can change it however you want. Sometimes you don't have to go by this whole thing. So what we'll do is first we will create the mesh. Okay. To create the mesh, you need to do block mesh. So that created my mesh. Now for a complex simulation, as Nikhil had, he would have done the decompose part. So for those decomposition part, you require an additional file as well. You can't just simply, if I were to type decompose par simply like this, it would not understand because this decompose par dict is not mentioned. Okay. So you need to copy a few of these decompose if you want to run it in parallel, or if you want to just do any additional things, you need to have those particular files as well. Now, this is a pretty simple case, so we don't really need to decompose anything. So let's just start the simulation. So to start the simulation in OpenFOAM, you always type in the solver name that can be found in your control dict. So whenever you open your control, you can always scroll on top and you can see the application. So in this way, you know which solver you're solving and what type of physics you're going to solve. So it's a good idea to always check this part out. So we'll do IcoFoam and then you just run. Now it ran really fast because it's a very small case, simple case. And then you do Parafoam to just visualize your data. Okay. Now, once it is open, we have on the top left, you would have U, P and all that. This is where you can change the parameters you want to see. So we can see the whole simulation. Now this is your simulation. Okay. But you don't really understand where are the recirculation and all that. So to view all of those, ParaView itself has multiple ways to see that. So on the just from where you clicked your U option or your velocity or pressure, over here, just below that, you have a few of these options. Okay. You have stream tracers, you have glyphs, you have additional, like if you have a 3D simulation and you want to view what's going on inside your simulation, like inside the domain, you can use the slice option. There is another clip option. And if you can't really find any of these, you go to filter on top over here. You click on filter and you type search. You just click on search. And then over here, you can type. Like if I want to type, say, tracer. So I'll type tracer and it'll give me here the stream tracer. Double click it or click and then press enter and then click apply. Okay. Now, Nikhil also had done something similar to this. Now we have too many streamlines. So let's lower this a bit. So say from 1000, I'll make it down to 100 and I'll click apply. Now, currently if you're doing this way, you are making or you are plotting those streamlines based on this line. But if you have a very, very long domain or a very large domain and you're trying to do this, it will always give you some errors or some weird spots. Okay. So there are different ways. You can either plot or you can remove the streamlines over this line, or on the left-hand side for seed type, you have an option of point source. So this point source will just generate a sphere. You can change the radius of the sphere over here down. So over here, let's say we make the sphere to 1. Okay, so we've made the sphere like really big. So I think 0.5 will be better. Okay. So when you're doing this, just make sure that your domain is completely covered, or at least the areas of interest that you're trying to remove streamlines around are covered. This is really handy for 3D cases as well, because this line is just a 2D line, right? It's just from point A to point B. But this sphere is in complete 3 dimensions. See, like, see, if you see this, it's in 3 dimensions. So if you have a 3D geometry, like a flow over a cylinder, 3D cylinder, a flow over an aircraft or airfoil or something like that in a 3D simulation, you can view the whole glyphs around the whole thing, around the whole geometry. So you will see we don't really have any demonstration schedule for the 3D case, because 3D cases do take a lot of time. But we have people who have already done most of the simulations, which are 3D simulations on our repo. So you can always check those also out. So, okay. So once we've done this, you can just hide this sphere, scroll in a bit and click on apply. Okay. Now 100 was really small. So let's bump it up back to 1000. Okay. So we have some problem. So say let's delete this one. Okay. Yeah. So we'll again do the streamlines. Go to point source. Increase this to 0. Sorry. This to 0.02 or 25. Okay. And 100. Okay. Yeah. Let's lower the sphere. Okay. Yeah. So you see over here we have some circulation, but in streamlines, it will just give you how the flow is happening. It won't give you an arrow direction or where exactly is the flow starting from, where is it going. For that, you can use the glyph option. Okay. So let's hide this one and let's open our cavity case again. And this time instead of stream tracer, we will click the glyph option. So you can click on glyph and over here you can assign, like now it is set to arrow. Orientation, you can set the orientation to u, that is your velocity, how the velocity will flow. In that way, these arrows will orient themselves. And then you have the scale array. The scale will just increase. Like we know that over here, you will have the highest amount of flow looking at the legend and the whole simulation and contours itself. Whereas over here, you'll have lower number of, like you'll have a slower velocity. So it will orient based on that, the scaling. For now, we'll just keep the scaling to no scale array and click on apply. You see over here, let's change the color a bit. Yeah. So see over here on top, since this lid was moving, and then over here, once it is moving, the velocity that is entering into this cavity, it will hit this wall, then it is hitting this wall, and then so on and so forth, and it's just circulating within this whole domain. Now, the same case, it is a transient solver. So until the simulation ends, it will keep doing this. Whereas for a steady state case, until it has like stabilized and everything is steady, it will give you your steady simulation case. And then once the whole domain is stabilized, it will stop the simulation. That is for a steady state case. So those are the basic difference between a steady state and a transient solvers or a transient simulation. So yeah, this is all about the cavity case in OpenFOAM 9. So the same, if you want to search tutorials in OpenFOAM 24.12, the path is a bit different. So under Ubuntu 22, this time instead of going to OPT, you can go down all the way to USR. And in this you have lib. Under lib, you scroll down, you can open OpenFOAM. And over here, you will have your OpenFOAM 2412. Same now, over here you have, now you see if you compare this particular tutorial directory and you compare the OpenFOAM 9, OpenFOAM 2412 will have more tutorials, more solvers, better solvers. Like you will have multiple solvers that are more stable and all compared to OpenFOAM 9. So again, if you want to modify anything, you can go over here to application, you can go to solver, you can also change utilities and all of those solvers over here. Now in our OpenFOAM 9, we only had basic. Here you have acoustic solvers as well, combustion, compressible, DNS, Then you have finite area, heat transfer, many solvers are there. So you're not bound to only be using OpenFOAM 9 for solver modification or something like that. You can use OpenFOAM 2412 as well. So this was just a brief and basic overview of OpenFOAM and how exactly are you supposed to copy files, place them in which files, how you're supposed to run, and the whole file structure and all that. So if you have any doubts, we'll be happy to take that now.
So this is the email ID of the CFD team of FOSSEE. Okay, if you, after this workshop, after we all log out, if you feel that you need to ask something, you need to post a question, you have any query, you can just drop an email. So just keep posting your queries here and we'll definitely get back to you.
Yeah, what solver is suitable for metal or polymer erosion? So for polymer erosion, mm, we haven't really tried any of those. Wait, just let me have a look. Erosion related, right? So you can try using one of the Lagrangian solvers because as Mr. Advait Gupta also said that they tried and they have used some of the modified Lagrangian approaches. So you can try using one of them depending on the case obviously you want to solve. Because we haven't really gone too much in detail about erosion and additive manufacturing as a whole. Harshada, if you are planning to create your own solver, yes, the user bin, the way that you've written it is fine. Okay, Harshada, if you are not able to see your OpenFOAM directory, just check whether your installation is done properly. Because if you have installed it properly, you will have an OpenFOAM file at least in your OPT file folder.
Yes, I am having OpenFOAM file,
Hmm.
but I am not able to see that OpenFOAM 9 and even though which version I have downloaded.
So have you downloaded any of the developer versions or the skeleton version? Because in those versions, you don't really get the tutorials. You can check which version, like OpenFOAM 9 is downloaded, yes, but just check the variant that you have downloaded in OpenFOAM 9 because there are specific versions for developers. There are specific versions in which you have just the skeleton, like you'll just have basic OpenFOAM files or libraries, and then you have the classic version that has all your tutorials and everything included. So just check which one have you installed. Okay, on the official website also you can search that. You can just type download Ubuntu Open or you can download OpenFOAM 9. You can click on for Ubuntu and then you can scroll down to their download page. On that they've mentioned all the versions and the variations in that particular version. Yeah, Paris has also given you a command. You can try running that. So for all of you who are starting off with OpenFOAM, unless you try using OpenFOAM, you won't really understand what exactly is happening because you have to get your hands dirty with OpenFOAM. You will get multiple errors in the beginning, but those errors will only help you better understand what you are doing. Because even I've used ANSYS and all of those commercial softwares. The thing about using a commercial software and using an open source software is that when you're using an open source software, you are solely responsible for everything that you do. In ANSYS and in any of the commercial solvers, you can at least say that, okay, in the backend, you have this particular limitation, so you can't really do anything. But in OpenFOAM, you have that entire liberty. You have everything you can do. So if something goes wrong, you have to sit and you have to see where exactly is the error. And it's not like as I showed you in the when we're doing our solver modification. If you get an error, the terminal specifies in which particular file on what line you're getting that error. So you can go line by line and see why is that error popping up. And then you can solve that. And there are multiple videos on how to solve these errors as well. So you're not really stuck at that point. Okay. So don't think that OpenFOAM is really scary and just because there's a terminal and all, it becomes difficult to understand. No, it's not like that. And also, we have been working on the front end for OpenFOAM at FOSSEE. So hopefully, in the coming years, we will have at least a GUI for at least the basic stuff. So you don't have to really rely completely on knowing each and every command. It might become at one point like ANSYS, you can just click some buttons and you will get at least a desirable output. So yeah, if there is any more doubts, you can ask us. We are there here, or you can type it in the chat box as well, which was comfortable. So are all of you trying OpenFOAM right now? At least the tutorial, the IcoFoam tutorial. Okay. So have all of you understood, or at least briefly understood, what we've done today, from the solver modification to multiphase? At least for undergrad, multiphase might be a bit difficult, but for people who are in their master's and PhD, are you able to understand what we are doing? If there is any improvement or something like that, you can always let us know. Miss Dr. Shekhar, you won't find OpenFOAM 2412 tutorials in OPT. You will have to scroll down to your USR folder. So wait, I'll share it again. So if you're trying to see anything for OpenFOAM 24, so you will have to go down to USR, and inside that you have to go to lib. Okay, just simple lib, and scroll down to OpenFOAM. Okay, so over here we have OpenFOAM. Click on OpenFOAM, and over here you will find OpenFOAM 2412. Inside this you will have your tutorials. Okay. Yes, Shruti, you have a doubt for the morning session. What exactly is the doubt? For people who want to learn about programming in OpenFOAM, there is a course by, not course, you can say, but a YouTube playlist by Mr. Tushar Gohil. He has explained everything from basic on how to do programming in OpenFOAM, how to develop your own solver from scratch as well. So you can check those videos out. And there's also Wolf Dynamics. They also have some documentation on solver modification and solver development. So those are also good. You can also check out the official OpenFOAM page. They have multiple resources for solver development as well. So these three places are your go-to place if you're trying to, or at least beginning with OpenFOAM programming and solver development and all that. Okay, I'll share the links over here. 1 minute, just give me a minute. Okay, Payal ma'am has sent one link.
Yeah, the other links you can share even.
Yes, ma'am. Okay, Shruti, you have solved for T and U, and you have also run the solver, right? The compiled solver. But your pipe is not visible in Parafoam. Okay. Shruti, once you copied the 50 folder, like whatever files were there inside your 50 folder into the 0 folder, the pipe geometry should still be created. Just try cleaning the whole case once again and see if that solves the issue. Try cleaning the whole case and run the whole simulation once more, because the pipe geometry should, if it is solving your equations and it is solving the whole simulation, your pipe geometry should be there. Otherwise, it would have thrown up an error at the very beginning if the geometry itself is missing. Or when you're loading it in ParaView, just check whether you're loading the proper file. Or you can manually do a touch.foam. You can create a file named .foam or something, and you can then open that in ParaView and see whether it is at least opening that particular file of yours in ParaView.
So can you please repeat it once again?
Okay, so try first cleaning the whole case. Do an all clean, like the bash all clean, which is already there in the file. Do that and run the simulation again and see if the simulation is giving any error. If it does not give you any error and it is running just fine, when you're opening it in ParaView, try to see whether the file that you've opened is first of all correct or not. Like, if is ParaView just not showing anything, or when you're clicking on apply, it is not showing anything.
So it's not showing anything, like the interface is getting open, but pipe is not visible. And even when I'm clicking on apply, nothing is visible.
Okay, but the file name is showing on the left hand side, right?
Yes, so file name has been shown.
Okay, so if nothing is showing, have you used ParaView before?
Yes, sir. For the demonstration, like when I downloaded the Ubuntu and then the Parafoam, no, then at that time I tried, then there was a geometry visible.
Okay. Okay, you can try using Parafoam built-in to just see if that solves the issue. I'll type the command.
So I tried using Paraform built-in. There's nothing visible. But when I just type Paraform, then it gives an error.
Okay. Okay. But while it is running the simulation, that time it does not give you any error.
No, so when it's running in PowerShell, there's no error. It completes whole process.
Okay. Because if it is giving you an error at the very last step, that is at least in ParaView when you're opening it and then you're trying to load the case and it says it gives you some error in red, right? In one box down.
Yes, sir. Yes, sir. In box.
So that is most probably because some file is missing, like you have either given a wrong boundary condition or some of the things are interfering with each other, or but then that should always give you an error at the very beginning. Like if you are solving your simulation, that is the time when you will get that error itself in your terminal. When you copied the 50 folder into your 0 folder, did you clear out the whole thing? Like is scalar 1 and scalar 2 still there?
So in 0 folder, I kept scalar 1 and scalar 2 as it is. I just copied T and U.
T and U, right?
Yes, sir.
Okay. And okay, solve for, and before that you already solved for U and for T.
Yes, sir.
And in the flow simulation, you've made those changes, right? You had to change the solver name also from simple form to scalar transport form.
Yes, sir. I have did that.
Okay, that is done. And then you've copied it into your folder and that is running. You've already used the all run script only, even for the new scalar transport form.
Yes, sir.
Okay. Can you share a screenshot of what error you're getting on the email? We'll try to see what exactly the error, because if it is running, everything is running fine, but your geometry is not loading and ParaView is giving that error at that time. So we'll have to first check whether it is running the simulation properly itself or not. Some file might be missing. That is why ParaView is not loading it and it is just giving you that blank ParaView.
Okay, sir. So should I share the screenshot of ParaView?
Share a screenshot of ParaView also, and when your simulation is done, no, whatever commands you're getting or whatever it's displaying in your terminal, once you've done your whole simulation, share a screenshot of that as well.
So should I rerun like simulation once again?
First try rerunning it. If you're rerunning it properly and then it works fine, then it's not a problem. If it is still giving that error, then you give these two screenshots on email.
Okay, sir. So like when we complete for the T constant, no, after that we need to copy whole 50 folder into the steady scalar file, in 0 folder, right?
Yes.
And in 0 folder we need to delete rest of the things. We need to only keep the scalar 1, scale 1, scalar 2, and T and U.
Yes.
Okay, sir. The process is fine. I don't know where the error is.
You can either delete or you can just keep everything that is there. Like whatever you're copying from your 50 folder, just copy and paste the whole thing in your new scalar transport form case, and make sure that your scalar 1 and scalar 2 are there as an addition to the previous files. Okay, try
Sir,
that.
like when I'm doing for T, then I don't get any new file for scalar 1 and scalar 2. The scalar 1 and scalar 2 are already there in this steady scalar file. So I'm not replacing scalar 1 and 2.
So you keep that scalar 1 and scalar 2 as it is, but just whatever is in that 50 folder, you just paste every single thing. Don't delete anything then.
Okay, sir. Okay, I'll do.
Yeah. Try that and see if that resolves the issue.
Okay, sir. Thank you, sir.